Welcome, everybody. It's April, and we're going to jump right into things because, again, we are on one of my nerdy favorites today. In particular, this is going to be part two on the Islamic Golden Age, and it will ultimately be the second of three parts because I just couldn't keep it down enough. I have too much that I want to say about the Islamic Golden Age. So remember, like we talked about last time, the Islamic Golden Age was this time of unbelievable flourishing in the arts, in intellectual life, in cultural life, and so on that happened in various Islamic empires over a 1400-year period. And today, we're going to be focusing on some of the achievements that happened during the third caliphate of the Islamic Golden Age, the Abbasid Caliphate. So remember, the Abbasids came to power in 750, and they were centered around the city of Baghdad, which was founded by the Caliph al-Mansur in 762, and interestingly enough, was founded on geometric principles. So during this time, Baghdad becomes the world's intellectual, cultural, and commercial center. And to give you a sense of what it was like, a visitor at the time once said, "No one is better educated than their scholars, better informed than their authorities in tradition, more solid in their syntax than their grammarians, more supple than their singers, more certain than their Quran readers, more expert than their physicians, more competent than their calligraphers, more clear than their logicians, more zealous than their ascetics, better jurists than their magistrates, or more eloquent than their preachers." And this unbelievable contribution ultimately can be brought to what was known as the Baghdad House of Wisdom, a place of learning, a place of scholarship, which housed two of the folks we'll be talking about today, al-Khwarizmi and al-Kindi. But it's important to note that there was lots of contributions in the House of Wisdom outside of these two. Some you might be interested in looking into was the famous translator and physician Hunayn ibn Ishaq, who tells us something interesting about the Abbasid Caliphate insofar as it was very multi-ethnic and very multi-religious. Hunayn ibn Ishaq, despite his prominence in this Islamic Caliphate, was himself a Christian. Similarly, you might be interested in looking into the Benu Musa brothers, who did really, really important work here during this time and were themselves Persian. So there's lots of awesome work we could ultimately talk about in relation to the House of Wisdom, but we're going to focus on mathematics because right now we're talking about STEM disciplines, and these STEM disciplines all ultimately have to use mathematics significantly. So we're going to start by talking about Muhammad ibn Musa al-Khwarizmi. So al-Khwarizmi was born in Baghdad around the time that Harun al-Rashid became caliph of the Abbasid Caliphate. He was an early head of the House of Wisdom and was appointed by the Caliph al-Ma'mun, who reigned from 813 to 833. And al-Khwarizmi is famous for work in astronomy, in geography, and in mathematics. But what he's most well known for is his work in mathematics, in particular two works, the Book of Addition and Subtraction according to the Hindu calculation, which focused on the Hindu-Arabic numeral system and ultimately helped introduce the Hindu-Arabic numerals to the Western world, and also his book, The Book of Restoring and Balancing. It's the latter of these works of al-Khwarizmi's that we're going to focus on. And the Arabic title of this book has the word al-Jabbar in it, which, for those of you who are interested in mathematics, should sound like a word that you are quite used to in mathematics, namely algebra. And this English word algebra ultimately traces back to al-Khwarizmi's work here and the Arabic word al-Jabbar. So when we're talking about algebra, we're talking about the study of arithmetic using and functions between both numbers and variables. That is, once we add in variables, we have algebra. So here are some particular expressions that have variables in them that bring us into the level of simple algebra. So variables, remember, can be used for multiple different purposes. They can be used to represent unknown quantities, or they can be used to represent generality. People talk about this latter function less, so I've given here an example where we might say something like, for all numbers x, x times 0 equals 0. There, x is not representing some unknown quantity, but x is representing any quantity whatsoever. So one of the things that's really interesting about algebra and the use of variables is it allows us to express infinitely many truths in a finite matter. So a case where a variable is used to represent an unknown quantity includes this example here, where we look at the algebraic equation 4x plus 7 equals 3x minus 18. So we can use some standard arithmetic operations to figure out what that unknown quantity x is. So if we subtract 3x from both sides of this equation, we'll get down to x plus 7 equals negative 18. Subtract 7 from both sides of this equation, and we will get the solution that x equals negative 25. So algebra gets used absolutely all over the place. And we have al-Khwarizmi's work to thank for that, because it was his work here that was the first dedicated study of algebra as a discipline unto itself. But it's not just the word algebra and work on algebra that we have to thank al-Khwarizmi for. Another word in the English language, which ultimately comes from al-Khwarizmi, is the word algorithm. So the Latinized version of al-Khwarizmi's name was algoritmi, hence the word algorithm. So when we're talking about algorithms, we're talking about step-by-step procedures for solving a problem which is guaranteed to yield a solution in a finite number of steps. And ultimately, we use this word algorithm as an homage to al-Khwarizmi because one of the things he accomplished in this work on algebra was algorithms for solving absolutely any linear or quadratic equation. So what I mean here is that an algebraic equation is linear if and only if the highest exponent on the variable is 1. So this example we've been working here, 4x plus 7 equals 3x minus 18, that's a linear equation. An algebraic equation is quadratic, on the other hand, if and only if the highest exponent on the variable is 2. So if we had an algebraic equation like 3x squared minus 12 equals 0, then we've got a quadratic equation. And again, one of the really interesting things that al-Khwarizmi does is he gives us completely general algorithms that tell us how to solve every single linear and every single quadratic equation. I've included here an algorithm for solving all linear equations that isn't quite the same as what al-Khwarizmi ultimately did, but it's in the spirit of his work. And that is, we need to start by paying attention to the form of the equation. And here, in this particular algorithm, we note that all linear equations can be put into a standard form of ax plus b equals 0. And then once we have that, we can subtract b from both sides of the equation to get ax equals negative b. And then we can divide both sides by a to get x equals negative b over a. And this algorithm is really nice because, again, it gives us infinitely many solutions to infinitely many equations. And again, this is something that al-Khwarizmi did in the 800s. One of the reasons I'm really interested in al-Khwarizmi's work is because he helps undermine this general stereotype that people have that somehow science and religion are at odds with one another. And one of the things that's really interesting here is that al-Khwarizmi's work on mathematics, on algebra, on algorithms was actually motivated, inspired by some particular Islamic concerns with running an Islamic empire. So here I want to give you an example of how this might have gone. So at this time, there were very many laws about inheritance in an Islamic empire. So let's imagine we have a woman who dies with a $60,000 estate, and she leaves behind a husband, 3 daughters, and a son. Inheritance laws around this time would have said that the husband gets 1/4 of the estate, and that each son gets twice what a daughter would receive. Now, the feminist in me obviously gets concerned by that, but it's helped out when I remember that around this time, daughters often got no inheritance whatsoever. So we can figure out precisely what each person should receive from this estate by doing some arithmetic and algebra. So the husband, remember, gets 1/4. So if we divide that 60,000 by 4, we get that the husband will get 15,000. So if we started with 60,000 and the husband gets 15,000, this leaves us with 45,000 left over. And here's where some algebra comes in. So remember, there are 3 daughters, and a son gets twice what a daughter would receive. So we have x representing how much each daughter will receive, and 2 times that, 2x, being what a son would receive here. So we add all of these parts together, and we get that 5x equals $45,000. So each part x is going to be 9,000. So we can conclude that each daughter will receive $9,000, the son will receive 18,000, and the husband 15,000. So again, not only is it the case that science and religion need not conflict, we have some examples here through al-Khwarizmi's work that religion can actually be a motivation for learning more science. And to have a further connection between science, religion, philosophy, we're going to look to another scholar from the Baghdad House of Wisdom. This time it will be Abu Yusuf Yaqub ibn Ishaq al-Kindi. So al-Kindi was known as the philosopher of the Arabs. And this was partly because a 10th century historian talking about him, Ibn al-Nadim, said he was unique in his knowledge of all the ancient sciences. So he was famous for contributions to mathematics, to logic, to cryptography, to astronomy, to medicine, to ethics, to psychology, to theology, and more. And one of the reasons he was able to have such broad contributions is because of the way he looked at knowledge. So he's quoted here as saying, "We ought not to be embarrassed about appreciating the truth and obtaining it wherever it comes from, even if it comes from races distant and nations different from us." So al-Kindi here was partly able to be so much more successful than anybody else in the world at this time because of his interest in diversity and pluralism and his willingness to learn from knowledge anywhere around the world, in addition to the knowledge that was around him. And in particular, he did work here both in Kalam and Falsafa, which we can think of Kalam and Falsafa as 2 different strains of philosophy that happened in the Abbasid Caliphate. So Kalam was something of an indigenous form of philosophy that's sometimes translated as Islamic speculative theology, whereas Falsafa, looking kind of like our word philosophy here, was philosophy as it was continued from the ancient Greeks. So we're going to take a look at a contribution of al-Kindi's that belongs to the Kalam tradition. And what's going to be really interesting about this is that it involves connecting theological issues, religious issues, with mathematical issues, with scientific issues. And in particular, this is al-Kindi's Kalam cosmological argument for the existence of God. And this is an argument that begins with the premise that all things that begin to exist have a cause or creator. And our concern here is going to be whether or not this applies to the universe. So al-Kindi considers the possibility that if the universe didn't begin to exist, that would mean that as we went back into the past, we would continue infinitely in this causal sequence back into the past. But Al-Kindi points out and will give us a really interesting argument that an infinite causal sequence back into the past is impossible. So that means that the universe must have began to exist. And if all things that begin to exist must have a cause or creator, and the universe began to exist, then the universe itself must have a cause or creator. And what could possibly be great enough to cause everything else in the universe to exist without itself having a cause? Al-Kindi says that must be God. And what's most interesting here about this particular argument is the argument that Al-Kindi gives for what I've called premise 3 here, that an infinite causal sequence back into the past is impossible. So Al-Kindi ultimately argues that we can't have an infinitely long universe because we can't have actually infinite anything. Because suppose we had something that was infinite, let's call this thing A. And now let's imagine we take some finite part of it away, B. Well, we need to think about what's left over, A minus B. If A minus B is finite, then the original thing A would have to be finite, because a finite thing plus a finite thing gives us a finite result. So that can't be. So that must mean that A minus B is infinite. But if A minus B is infinite, then A minus B, something strictly smaller than A, is of the same size as A because A was also infinite. So here, Al-Kindi tries to show us that there can't possibly be anything infinite because we end up with impossible results either way. Now, it's interesting to note that even though Al-Kindi seems to be wrong here about the infinite, his argument about the infinite shows an understanding of the infinite that would not be achieved for at least another 1,000 years. This is actually now how mathematicians often define the infinite. We say an infinite collection is one that is so large that even if we take some pieces away from it, it still stays the same size. So again, this argument for the existence of God ultimately gets us into some really interesting stuff with respect to mathematics, but it also gets into really interesting issues in relation to science. Because notice this sub-conclusion here that the universe began to exist seems to be what the scientists are telling us these days. Furthermore, this premise that all things that begin to exist have a cause or creator seems to be something like a modern scientific worldview. The idea that nothing happens haphazardly, the world is one big causal nexus. So again, the idea that science and religion, mathematics and religion, philosophy and religion somehow need to be at odds with each other just doesn't seem to fit here. So, we'll talk about the Islamic Golden Age some more in a couple days, but before, I want to leave you with some more music. And again, as we go further, I'm going to give you more and more difficult examples of music here. So I'd be interested if you can try to figure out what connection I was making between this song and what we ultimately talked about today. So this is going to be a song by DJ Cheb Sabbah called Qalanderi.